Thanks, everyone. It's a pleasure to be here. I wanted to explore the full glory of Sweden, so I went to Kisbo. Is that Abisko? Abisko. Sorry, I got over the weekend and got to see some of the northern lights. So that was a lot of fun. But I've enjoyed the time here. I came for the advisory board meeting last week, and it's been a good visit. So just let me jump right into it. So please feel free to ask questions as well along the way. So, my quick overview is recent trends in extreme scale HPC paint a really ambiguous future for where we're headed in terms of architectures and programming models. And I'll quickly just talk about Denard and more, but only one slide. I think the bigger picture is the ideas of markets and the business trends are really what's going to drive the changes over the next few years. And this is simple things like the price of DRAM doubling over the past year, as well as global foundries deciding not to go to 7 nanometers. It's going to force a lot of changes in the systems we have. And this includes things like the I/O is really plateauing, at least on the systems that we see. Someone's going to have to find a way to compensate for that. You can't just keep increasing the size of the systems and keep the I/O rates constant. So I'm going to argue that the major transitions are underway now, and the applications teams are really going to have to adapt or risk being left behind. And we have examples of that right now in DOE, where some people have been waiting for the heterogeneous computing craze to pass, and then they'll just get on with their work with regular CPU codes, and they're being left behind. And so what I'm going to argue is that we ought to enable that by looking at programming models and tools to help people to understand how to use their codes. The main challenge is complexity is the next major hurdle. Memory systems are rapidly changing. They've already started to change. Some of this is hidden from you. Some of it is yet to come. But we're going to see new devices, new system organizations, and new configurations of memories that we really haven't seen before or haven't had much experience with. In order to manage this complexity, we really need design tools to help build the right architecture, which is a lot more challenging than it used to be. And then programming systems must support these new memory systems. And right now, I mean, if an application team comes to you and says, how do I program the different memories that I see just on today's architecture? Shared memory in a GPU, HBM on KNL, non-volatile memory in the node. There's not a good answer, right? It's pretty much all over the map. And so we need techniques that we can use to mitigate that challenge. And so I'll argue that the memory systems themselves are really going to fundamentally redesign the architectures over the coming years and thus force some change in the applications themselves. So before I do that, I just wanted to quickly say what Oak Ridge was anytime I travel internationally. So Oak Ridge is mainly a Department of Energy laboratory. And that's just a U.S. organization that does basic science along with stockpile stewardship and some other things in the U.S. There are a lot of labs. 3 NNSA labs are Sandia, Livermore, and Los Alamos. The others are mainly Office of Science laboratories whose main goal is open science. Oak Ridge is the largest open science lab, and that includes Argonne as well as Lawrence Berkeley Lab. Oak Ridge does a lot of things. There are, of course, computing, which I'll talk a lot more about in a moment, but we have one of the largest scientific instruments in the world in SNS. We have about 5,000 employees, and we do a lot of work in materials that dates back to our being part of the Manhattan Project. And we have a lot of people working there. If anybody can see, there's a Swedish flag in there. So this is a snapshot of all the different employees that work at the laboratory, nationalities of all the employees that work at the laboratory. So And we host a lot of visitors. So if you're ever in the area and you want to come and visit, please reach out and we can make that happen. So major trends in computing. Let's talk more about where we're headed. So this slide, many people have seen. I don't want to spend too much time on it, but if you talk to a lot of people who are in device and architectures, you know, they argue that it's getting a lot more difficult to build transistors, just because the tools we have and the materials that we use are getting much more difficult to predict and model at these levels, and at some point it just becomes too expensive. And so we've all heard these arguments. We know Denard's scaling's already stopped, and Moore's is starting to slow down quite a bit. If you look at the business climate itself, and this is just snapshots of things that I grabbed that over time, you see a lot of things happening in the semiconductor industry. This includes just a lot of mergers, a lot of acquisitions, companies changing plans basically overnight that can really impact where we're headed. Companies becoming chip manufacturers, right? Companies like Amazon and Google building their own chips, other organizations doing this. This, you know, I think indicates that there's a lot of turmoil in the area right now, and supports that idea that the cost and complexity are very hard to manage. Overall, I think I love this chart by Ray Kurzweil out of his book where he talks about different phases of computing. But if you look at this, I really think we're entering the sixth wave over here. We've had this great run of about 50 years of the integrated circuit, transistors, and we're starting to see this breakdown. So we're moving into this sixth wave. And I think this is really the way we ought to think about it. We ought to think of the technology as we're going to see something new coming, but how we manage this transition is going to be good for computer scientists, but it's also going to be full of risk and other challenges. And if you look at these types of transitions, I basically categorize them into three things. The first one is, okay, we've been doing this for a while. I think it's going to become even more vital. That is optimize software and expose new types of parallelism. And that's kind of what we've been doing with GPUs, right, for the past few years. And we're going to be doing it even more as we see new types of architectures come out. This also includes things like, you know, taking that Python code you've been using for a long time and actually making it a kernel, or making it something that runs very fast. And there's a lot of code out there like that. The second thing that's really exciting right now is this idea of architectural specialization and integration. And it's really, I mean, CMOS is a wonderful technology if you get right down to it. It is a very effective, systematic, predictable way to build chips. And so that's something that's we won't lose. We're going to integrate them in different ways and build different types of ASICs. And then finally, the one that gets a lot of attention, especially in the United States lately, is new types of computational paradigms. And that's quantum computing, neuromorphic, advanced digital, and what I'm going to talk about today, emerging memory devices. The advanced digital really means taking digital technology to the next step with something other than CMOS, and that could be something like carbon nanotube transistors, which DARPA just invested $60 million in. So if we look at this in just a step, the architectural integration and specialization, you know, you guys are in the area. You've seen these things coming. We've got GPUs. We've got Google. We've had Anton and HPC for a while that showed phenomenal speed ups on protein folding problems. And we've all used FPGAs at one point or another. And just recently, if you go to like hot chips, there's a whole new set of devices coming that are far beyond x86. I think the most interesting one is probably the new Boom core that's from the RISC-V open instruction set. But then you've got other things like this Xavier, which is the NVIDIA's next system on a chip. It includes deep learning accelerator and vision accelerator and Volta cores and just many different types of capabilities. And then you have Xilinx announcing their Everest project, which is like a coarse grain reconfigurable system. And this is all, all of these are products. They're not just research ideas. They're things that we're going to be able to buy or use in the very near future. And of course, the Turing Award lecture guys, Hennessy and Patterson, they're talking about hardware, software co-design and agile chip development. This looks like some of the DARPA slides we saw a few weeks ago where, you basically check your technology out of GitHub, use some tools to put your chip together, ship it off to an Amazon-like facility, and 2 weeks later you get the board and chip in the mail and you plug it in and start using it. And that's really what DARPA is thinking about, actually making that process so easy and fluid that you could do that. The emerging technologies is the other thing that's happening that's very exciting. The US just started a quantum initiative to spend billions of dollars. Of course, the Chinese and others here in Europe have been investing heavily. What I'm going to talk about is emerging memory devices. And this is just a snapshot. I was amazed one day when I woke up and CNBC, which is the business network, had a session on quantum computing for finance, right? That was, they were all sitting around talking about that the same way they talk about things like, how many sodas did Coca-Cola sell last year, right? And here they're talking about how viable quantum computing is. So the question with the emerging technologies is the following. If you really look at this transition period, some of these technologies are going to be a lot more disruptive than others. If you take something like a new type of switch or a new type of transistor, it's entirely possible that users don't know anything about it. These carbon nanotube-based transistors that I mentioned earlier, it could be they just slide them in under the hood and have an instruction set and an architecture that looks exactly like what we have today. However, if you look at things like quantum computing, you may have to completely redesign your algorithms for that. There may not be an easy answer to mapping your codes onto that. And what this chart here shows is a coarse attempt to try to understand what those disruptions are going to be. And then you have things like non-volatile memory and neuromorphic and approximate computing that give you some indication of what disruptions will be at each level. So that's the broader. I haven't been talking about just HPC. I've been talking about computing in general. And so what we're seeing in HPC is exactly the same. So this chart illustrates a snapshot of the architectures that DOE Office of Science is building. And what you see here is the systems from, say the past 5 years or so, and what their main architectural components are. And then what we have coming up, right? And the purple highlights really the areas of major change. So the first one is this idea of multi-level memories and multiple types of memory. In the old days, you had DDR, right? And you had main memory, and that was it. Now, all the systems we're buying have on the order of 3 new memories, and that's memories that may not even include the things like shared memory and GPUs. They're high bandwidth memory, persistent memory, and DDR, for example. And then, on top of that, you have the different heterogeneous cores that we're all familiar with. And again, this is changing. Just Aurora, for example, many of you know, was postponed because Intel decided they didn't want to build Knights Hill. And so now, there's a new design underway, but it'll be different than what we've been targeting. And so that's something that as people buying these systems and using these systems, we're going to have to be agile and able to adapt to quickly. And then finally, you've got the I/O. And I just put this one in here to emphasize the point about memory. These systems are growing at a pretty significant rate. And we expect, an Exascale system in about the 2022 timeframe. The I/O bandwidths are not growing at all. I mean, in the, 1 terabyte per second has been what we've used for the past several years. Summit's going to have 2.5, so it's not even doubling as we go to this new system. Meanwhile, we're going up not quite 10x in overall peak and things like memory size, but it's a major challenge. We have to think about how to use that memory differently. When we introduced Summit, Summit hasn't been accepted yet. It's not quite open for business, but it's on the floor and running acceptance tests now. And our lab likes to have big events, so we had the dignitaries from the office and NVIDIA and IBM there to talk about it. The overview, which I'm sure many of you have seen, is the Summit nodes are very GPU heavy, and it looks pretty much like a symmetric system. If you just divide this line and fold it across, that's kind of the way you want to think about it when you're programming it. You've got one Power 9 hooked up to 3 Voltas, and those Voltas have a lot of capability. HBM, they've got a lot of bandwidth to the GPU, and these are the Volta GPUs that include the tensor cores. There is non-volatile memory on the nodes, and they are using InfiniBand as their dual rail InfiniBand as their interconnect. That's Summit. The next system is Frontier, and in one of the earlier charts I talked about the Exascale systems. So Summit should be available starting this fall for general production use, and we expect that to last through about 2023. The new system we've already received RFPs for, or proposals for an RFP, and so that should be announced maybe by supercomputing, but it may drift past that. And then the build, the non-reoccurring engineering costs, and all the preparation will start for Frontier, and we expect Frontier to be available sometime in this time frame of 2022. So, I'll argue this 6-wave transition, I think complexity is really the main challenge. And the two that I'm focusing on are these questions of, how do we design future systems so that they're better than the current systems? So I expect some challenges in procurements over the next 5 years, right? There's going to be systems that that are built that may not be as fast as the old systems we have on the floor. And we've already seen examples of that. The second thing is, how do we design applications with some level of performance portability? The software, after all, lasts much longer than the transient platforms that are swapped in and out between them. This is where we get back to this adapter die. I mean, it's getting to that point. Yes?
Why aren't you taking software into the equation as we change in hardware? It might be a transition period for software. That might not hold any longer. Especially when we talk about software, hardware, code design. Mm-hmm. It might be the case that software also becomes a one-off thing. We use it and then we have to start from scratch.
Right. Well, a lot of people don't like that answer, right? So I agree. I mean, so the biggest, one of the biggest success stories in software over the past decade has been CUDA. So CUDA has been something that's been very popular. A lot of people using NVIDIA GPUs work well with it. What if the next system we buy is not a CUDA system? What do we tell all those people, right? They're selling a lot of chips for machine learning and things like that, and it may be that we have to buy some other type of system. And so we've got all these millions of lines of source code. How do we convince them that they change their applications?
Right? So
yeah, sure.
NVIDIA put tensor cores. right? Which means that you might be close to Exascale if you do 8-bit or 4-bit floating point. And you have an application that can do that. And you use it. You use the tensor cores to Exascale right now.
Right.
Right? Well, next iteration, NVIDIA might separate the GPU from the tensor cores and have two different accelerators that are not.
That's an interesting thought, yeah. So, so you'd have to change something in the code or change the architecture somehow, right? So I agree with you. And now, so, I mean, this is my point.
We can go on.
Yeah, sure.
We better take it offline.
No, I think there are different levels of software too. If there are libraries and other things that can be identified, that makes the transition a lot easier, right? So this is one of the things that I'm not able to share completely yet, but earlier this year we had a workshop on extreme heterogeneity. And so we got, on the order of 150 or 200 people together, including academics and others, and tried to go through this thought that many dimensions of the system are starting to change now. What needs to happen? We're already behind. What do we got to, how do we confront this challenge? And so that'll be coming out maybe in the next 2 weeks. But what the output of this process is what we call priority research directions. And we came up with 5. And those 5, this is the official slide the program manager used when she was describing it, so I can put this up and not get in trouble, is really maintaining and improving programmer productivity, managing resources intelligently, modeling and predicting performance. Like I mentioned earlier, it's becoming a lot more difficult to know what the final performance is going to be on a system. This one really jumped out, enabling reproducible science despite non-determinism and asynchrony. So if you've got all these components and they're all adapting and maybe using different ways of doing floating point, how can you reproduce that answer that you got earlier? That's something, and then you think about errors and mitigating those, and it gets more complicated in these complex architectures. And then the final one is facilitating data management, analytics, and workflows. And that's really similar to managing resources intelligently, but this is a much higher level, like a geographically distributed system. I don't want to spend too much time on these. The managing resources intelligently, I'll just say a little bit more about. That's really about discovering new resources in the system and being able to schedule them on the fly so that oh, I have a new SoC that has a vision learning accelerator or a FFT accelerator in it. How do you discover that and map to it unless you've written a code to actually go do that? That can be a challenging problem that we can't really do right now. So with that, I'm going to go and jump into memory systems. Does anyone else have questions about the general feeling of what I'm motivating here? Most of you are familiar with computer architecture, so you're probably, hopefully your agreement with me that this is a big challenge and a big opportunity. So let's take a moment and look at emerging memory systems. So we started a project, it's been almost 9 years ago now, looking at non-volatile memory in future systems. And since that time, memory has changed a lot. If you look at just the marketplace in general, there used to be a time when you had DDR and then maybe graphics DDR and some low power, but that's all really started to fragment. If you go out and look at all the different memories you can buy now, it's really starting to fragment to serve different markets and different costs and power requirements. And so that's just happening today. Then you have all of these new materials and new devices on the market, and they're starting to appear. MRAM, for example, is actually starting to be shipped in production. And then, of course, you have things like 3D NAND flash, and then Optane from Intel, to most people think it's PC RAM. Intel hasn't let the word out on what it is exactly yet, but everyone thinks it's some version of phase change memory. They're all different in terms of access times, read-write times, latencies, power, durability. And so what this chart here shows is just kind of how varied those types of memories are. And they're things that we're going to have to learn how to use again and optimize for again. I love this chart from iMech that I grabbed earlier this year, and it really shows you the complexity in the coming systems. So if you just look at the storage hierarchy and think about all the options you have at different levels of the storage hierarchy, there are a lot of options. Things like Faro DRAM that's non-volatile, and you might be able to use it completely differently than you did normal DRAM. We need to investigate those and understand where they're headed. And then again, I go back to market forces because we're just HPC. We're not going to change the marketplace by ourselves. But this is where non-volatile memory is being driven largely by the consumer marketplace and the enterprise marketplace. And if you look at just simple things like these SD cards, right? They're incredible. I mean, I just picked this one up last weekend. I took a picture of it last weekend. 400 gigabytes for $99, right? It's a half a terabyte almost for about $100. And then you have a bunch of other technologies like the Optane, and Samsung had this other breakout product. They're claiming they're going to have 128 terabyte SSDs soon, and then that's going to ramp up from there. So if you think about how much 128 terabytes is and just what the bandwidth would be to put something on 128 terabytes, it's pretty incredible. And so, in fact, if you think about the different hierarchies, if you think about 128 terabytes of non-volatile memory per node of a scalable system, you have about 7,000 nodes, you could have an exabyte of memory. That's something that people really haven't thought about for a long time. They've thought about an exascale system, but they haven't thought about a system with an exabyte of memory in it. And it's completely possible with these new Samsung drives that you could have an exabyte of memory in these systems. But then I get back to the part about how long it would take to transfer. And that's where you have to worry about I/O. Even in the perfect case of having a terabyte per second, it would take 11 days to dump all that data out over that link. And that's just, a bad trend.
Sorry, excuse me.
Sure.
11 days when all these 7,000 nodes work at 1 terabyte per second.
Go out through a 1 terabyte link. So that's kind of the way the systems are set up now. They have, they usually funnel the I/O out over some number of I/O nodes that collectively give you like 1 terabyte per second to a SAN, and so that's what these do. So we have a project, as I mentioned, looking at the integrated solutions. I'm not going to have time to talk about these today, but I wanted to mention several of them. So the first one is really building the right memory system architecture. And so this is something that we've been thinking about a lot because we've had people propose some pretty wild architectures lately. And we don't even know if they're feasible to build. So what this top chart shows is just if you have 3 types of memory, you have some off-chip high-performance memory, some volatile capacity memory, and then some persistent capacity memory. What should be the architecture of those? So here, this represents just a vertical organization where you have some type of cache-based organization or paging organization. And these represent more scratchpad managed memories. So the user has to understand where to put them, and we call those horizontal memories. And then you have all different types of combinations, and you know, some of these we've already seen. If you go talk to someone like Bruce Jacob at the University of Maryland, for years he's talked about having just some high performance memory in front of, you know, just petabytes of flash. And that's all you have. There is no other memory, and there is no DDR in the system. Meanwhile, you have others that have something that look like these. Knight's Landing over here, for example, could have something like this, or even perhaps go out to persistent capacity memory. And this is just a table showing you what the differences are. It also comes down to budget. You know, if you have a certain budget, each one of these is going to cost some different amount of dollars per gigabyte, and you have to balance that out basically with your application's needs. And so what we did with Ivy, in fact, recent graduate, was build a system to try and understand this. And so if you look at one of the challenges in doing this, if you take a simulation of a big scientific code and run it through GEM5 or even ZSIM or some of the lighter weight simulators, it still runs too slow to do a parameter sweep of many different configurations. And so one of the things that we did was actually create a front end called Siena. And what Siena does is use abstractions for the application model. That's important because we want to be able to change the sizes of the data structures, the amount of computation and so on that's going on in the actual application. And then that generates streams of loads and stores. And those loads and stores then get grouped together, scheduled, dispatched. They go through a cache filter and go out and hit these different memories. And down here we use things like NVSIM or Ramulator or DramSim to simulate a specific memory that we're targeting for that. In the vertical organization, it's relatively straightforward because you don't, have to be involved with actually mapping the data into different memories. You can do that with the paging and caching mechanisms. But in the horizontal, it becomes a bit more challenging because what we do there is actually take the different data structures within an application and map them into different memories. And over time, we've really found this is something that could be important, especially for non-volatile memory. In this graphic, which is, it's hard to dive into all of this because it talks about many different mappings, but if, for example, if you look at a DDR plus an HPM, a high performance memory of some type, and then you try different mappings where you're mapping different parts of the data structure into different types of memory, basically we want to sweep through all those and find out which ones are good probability targets to investigate in deeper detail. And that includes sweeping over them for placing them in the different memories, plus the different parameters. And so we changed the application's data size, for example, to make it a bigger problem, to make sure it wasn't all being stored in cache. And so when we looked at that, again, this is a snapshot. A specific instance of our result is not what we're after here. We're after the overall trends. And so a specific instance is shown here where we're actually looking at this data. These are the different mappings of data structures to memories. And then this is the latency and the normalized performance. And so what you see is, some of these mappings provide really poor responses. M3 and M4, M6 and M7 are doing well. There are others that are not doing very well. So the idea would be that by sweeping across this space quickly, you'd be able to eliminate the ones that just don't perform well. Bruce Jacobs' design didn't perform very well, having a lot of flash and HPM. But there's a lot of work left to do. The qualitative summary really gives you an idea of what the sensitivities of these applications are to the different parts of the memory organization, such as whether it would perform well in a vertical memory organization or a horizontal memory organization, and how much it would use HPM, the high performance memory, when it's configured that way. And that has to do with locality, and there are a lot of other metrics that we talk about in the paper that help identify that. But this is really the overall goal of the study. Okay? So that was the first step, is how do we build the right systems, given a diversity of applications and technologies. The second one is really how do we program these non-volatile memory systems portably, and this is something everybody's been thinking about lately. So the first thing is really thinking about how we're going to use non-volatile memory in a future system, and we focused mainly on non-volatile memory recently. They're burst buffers, and these have been around for several years. They really hide behind the I/O interface and push that data management out through the library interface and in most cases the MPI interface to store up the output data and then drain it off to the storage area network. There's some other interesting techniques being looked at that use in situ visualization and analytics. And that really means, instead of writing all your data out to that SAN and then coming back and reading it all back in later to make your movie or do your analytics, you just store it in that non-volatile memory. Because you've got, let's say 128 terabytes. So you write it there and then you come back and make your movie, so there's almost no cost to doing the I/O. Especially over that slow link that I mentioned. And then the one that we've been exploring is this idea of persistent data structures like materials tables. So in a study we did several years ago, we found codes like NEC 5000 and some others. If you looked at the real codes and not the mini apps, you found that they had large tables that they referenced constantly in their loops. These can be things like materials tables or geometry arrays or isotope tables, and sometimes they're multidimensional so they can get quite large. In a lot of cases, those would be great candidates to put in non-volatile memory because remember, you're talking about cost and you want to reserve your DRAM for that memory that you need reasonably high performance on. If there's something that you can store in non-volatile memory and access relatively infrequently, that's what you should do. If you look at this blue mark here, and they're both on the same graphs here, this shows about 30% of the data object accesses in NEC 5000 are read-only. Basically, they get read in and then from disk or calculated, and then they're just read-only after that. So those would make a great candidate for non-volatile memory. So now and there's other ways to use them. There's a lot of people looking at this problem right now. So if you think about, okay, now I've got some scenarios, how do I want to actually program these systems? There's several decisions you have to make. Where's non-volatile memory in the system? Is it on some data warp nodes that are remote in a different rack? Are they local? Are they in a DIMM slot? There's questions about where it's stored. Where it's integrated. And then you have this question of exploiting persistence. Now, the non-volatile memories don't cost you anything when they aren't being accessed. But the question is that something you want to make use of? Or do you just swap it in where you had DRAM or some other memory just to save on power and cost, for example? And some people want to do that. They don't really want to worry about the persistence. But if you do want to worry about the persistence, you really have to start thinking like a file system or a database person and start thinking about these ACID semantics that we all learned about in our databases classes.
Quick question.
Yes.
So persistence is about crashes, right? If you can recover things after a crash, the node goes out.
Right.
Can you save what was in its persistent memory?
Right.
It was written in the right order. What's the overhead in a large production system? What's the overhead of checkpointing that you do?
It's significant in the sense that it has to go out over that I/O link that I was talking about earlier. So the cost is really in the I/O. of writing it out. That's in a traditional system. You had DRAM. There was no local storage. There was not even a local disk in the past decade, and so that had to go out over a link, and so you were limited by your bandwidths and things there. Most people, most checkpoint data is not read, right? It's written, and so it goes, and if everything goes well, it may not be read. The checkpointing here is, one of the things that we're going to talk about in a moment is, I see maybe a completely new way to start thinking about checkpointing, and you're not thinking about it in a way I'm writing defensively to just guard against a crash, but you have this big persistent data structure you're just updating the state to. And if you die, it's no big deal because that big persistent data structure, will still be there. And you can go back and start accessing it.
Yeah, so the question is, if persistence costs less than what checkpointing costs today as overhead,
right,
then that's fine. Otherwise, it's not, right? So my question is checkpointing absolutely necessary in the high performance world? Everybody does it? Is this?
Yeah, it is, and it depends on what kind of checkpointing you're talking about. Most people have application data that they do both productive and defensive I/O with, and the productive is they're generating a movie or they're analyzing results, and defensive is the checkpointing in case I crash. A lot of times those are the same for users, right? And so they're going to be writing these out anyway. But then what this allows you to do is store it all locally in faster memory and not have to write it out over that link, because there's a lot of intermediate results that also can be analyzed along the way. So I'm just going to mention 3 things that we're working on just to give you a better idea of what I'm talking about here, and I'll do that pretty quickly. So the first one is non-volatile memory. So there's it'd be nice if we could just hide this from the user. Remember the disruptions I was talking about earlier, and I said, boy, if you could just slide it in under the hood, no one knew about it, that would be really nice. Well, that's what we're trying to do with GPUs. So GPUs have historically had this challenge of limited memory, and you had to, back pre-Petascale days, you had to write some fancy code to transfer the data from maybe a file into host memory, and then host memory into the GPU, and it was really complicated. Recent GPUs have added this paging support to host memory, and that's a big improvement. But then the data sets we've seen grow larger and larger, and all you got to do is look at the machine learning world to see the data sets grow to be terabytes in some cases. So what we've done is extend GPUs to use non-volatile memory using the same paging support. And so it really allows you to have unlimited access to the memory and the non-volatile memory from the CUDA kernels. We've added some support for temporary and read-only data, and we get good performance, in some cases surprisingly good performance. The way this works, just to walk through it really quickly, is the user doesn't change a CUDA kernel at all. So the CUDA kernel is unchanged. What they have to change is just the mapping of the input files to load the data from non-volatile memory. And there's a couple calls that we have that you do when you initialize or finalize your application. Whenever there's a page miss, it goes out and a page fault gets captured by the host. The host finds out if it has it locally. If it doesn't, then it can reach out to non-volatile memory storage and pull that page in and then pull it into the GPU. And we do things in here like read ahead. That's all part of Linux, and there are things like asynchronous write back that make it durable by flushing it back out to non-volatile memory. And initially we didn't know how good this was going to be. Again, there's a lot of results in the paper we're going to have, including we use some cafe image and video benchmarks in the paper that use Facebook video benchmarks and things like that. But what this table really shows you, and what I want to emphasize here, is that in the old days, your GPU memory was limited to this size, and so the data that you see here in the first bar is really just running inside the GPU. The second one is when you use registered memory, and the third one is when you use managed memory. And the fourth one is Dragon, okay? That's the name of our software. So what Dragon allows you to do is scale this up so you're running completely out of non-volatile memory. And as you can see, some of these other techniques basically stop when you get to either the GPU border or to the host memory border. And what we've done with managed memory, for example, is estimated what it would perform like, because it doesn't work with non-volatile memory right now. And so this scale could continue going up to terabytes here if we wanted. The two takeaways from this is, if you have anything that resembles predictability in your memory access patterns, it's a win. In some cases, we do better than just the vanilla drivers that NVIDIA has in place. If you have irregular memory accesses, it can also be a win, because what happens is the kernel and the paging mechanism can start all those data transfers far faster than a user could by writing the code themselves. So they're not really waiting on the user to fire those up. The page table just starts the transfers immediately. And then finally, there's just some codes that are just horrible in terms of memory access pattern. And they're never, even the user can't write good code for it, right? And so there's, a lot of data here. I don't have time to get down into it in too much detail, but the driver's on GitHub, and we're happy to share it with anyone who's interested in collaborating on this. So that's the transparent way. So the second way is language support. So one of the things I mentioned earlier was you have NEC 5000 and it has these tables in it. If the user knows they're going to be read-only tables, have the user just put them in non-volatile memory, right? Why try and guess or figure it out on your own? So one of the things that we've been working on is this novel C. And just briefly, it's extensions to the C language, including a type qualifier and then some pragmas. And the type qualifier lets you declare a non-volatile memory pointer. And that non-volatile memory pointer then can be type checked and other things used for optimization so that it performs well. Then, as we mentioned earlier, with the durable data structures, you need things like transactions, and so we created both redo and undo logging support for transactions, so your read and write sets can be accumulated and managed by the compiler itself. And then that gets all compiled and run with the runtime system. Originally, we targeted the PMEM library from Intel. They just made a new name for that, but I can't remember what it is off the top of my head. But the nice thing about this is you can create these non-volatile memory heaps in your program. And at the end of the day, they can look pretty much like a file, but you open those and then you basically have pointer access into them. These are the different types of pointers you can have. Some of them don't make sense or are difficult to manage. So this is where the type checking can help. You can have, of course, pointers to other data elements within the same heap, but you can't cross heaps. You don't want a pointer pointing back to volatile memory from non-volatile memory, because that doesn't make any sense. You never know who's going to be loading you from the non-volatile heap perspective. And then the volatile memory one is pretty clear. The transactions, I just wanted to mention quickly here. Right now, this is a simple example that fits on a slide, but you can do things like have non-volatile memory pointers for all of these, and that means they're durable. They are in that non-volatile memory heap that I mentioned, and then you can protect them with transactions. So in this example, which we talk a little bit more about in our paper, there's a transaction for every iteration in this loop. So all the data that gets written in this block is made durable at the same time. It either all gets changed or none of it gets changed. And so if there's some kind of crash or something that happens, then you know you have a consistent data set to come back and start with. And so this is where the idea of the checkpointing and restart comes from. And we've done several optimizations on this. There are things like aggregating transactions and hoisting some of the transactions up to a higher level when you know it's a good thing to do from a performance perspective. So just speeding along here, the last thing I wanted to mention is kind of at the highest level. So the first two were something we could put on a simple workstation and let someone use. We're an HPC, so when you think about having 7,000 nodes, each with 128 terabytes of non-volatile memory on them, you know, what could you do with that? And so one of the things we've been working on is a project called Papyrus, and what it does is take those non-volatile memory architectures and really abstract them away from the users. This gets back to the performance portability argument. So our Cori system at NERSC has burst buffer nodes, and so it's non-volatile memory, but it's just, you know, racks of non-volatile memory that the compute nodes hook to. On Summit, the non-volatile memory is all local to a node. What Papyrus does is really take that visibility into what architecture you're running on away, and the user just sees things like maps, vectors, and matrices at the higher level. So there's no, you know, real porting when you go from from system to system, and it's hidden from the user. There are things that we actually enable here. One of those is relaxed consistency model, and this is, if you know UPC or some global arrays programming models, PGAS programming models, you know relaxed consistency is important for scalability. And so what we've done here is the same thing, so that you can make changes to these. And remember, you're in control. It's the same story with relaxed consistency. You got to be careful what you're doing, but if you do that, we see good scalability. And then you have a fence operator or barrier that then will flush all that out and update all the metadata. The one thing that was a surprise was key value stores. So how many scientific applications use key value stores? Well, when my guys asked me this, I was like, none of them use key values, right? And so, but I said, okay, go ahead and have fun, see what you can do. And so they built a nice key value interface to Papyrus that we call Papyrus KV. And what it does is really use the key value paradigm to have a global shared tuple space, if you want to think of it that way. And it also has this relaxed consistency model. And I'll just show you an example of what an operation looks like. And it's nice because if you look over here and think you're an MPI operation and you want to grab some data, you know, you can. It may be locally because you've cached it somewhere, and so we first check there. If not, then we go out over the interconnection network and go to the location that it's hashed to, and then grab that value there. It could be in DRAM there, but it could also be in non-volatile memory. And so if it's not here, we reach out and grab it out of non-volatile memory and bring it back through that chain. And what happens when you have a fence operator or a barrier, it actually flushes this whole channel out. So it makes sure after the fence that any changes you've made are stored in non-volatile memory. And the reason for that is that we really wanted a way to start doing the checkpointing and start thinking about new ways to ensure consistency in application results. And so one of the things that we're doing now is working with applications teams, and in the Exascale computing project, we grabbed this miraculous benchmark from Berkeley. This you can download off the web. It's a UPC application that does part of the sequencing and assembly for biomedical applications. So what we did was we went in, and since it's written in UPC, we created another big table. It was just a key value table. And what we used were keys, were the sequences we were trying to match up with, and then the values were stored and scattered across the system. You could go out and look up anything in the catalog just using your normal key value store, and that was the way you operated. The benefit of that is we were able to eliminate about 500 lines of UPC code, because in the UPC code they had written optimizations for distributed hash tables. A key value store, our key value store, is a distributed hash table. So we were able to basically reduce the size of the code by about 10% just by switching to our API. What we see is the performance is good. It's not yet as fast as UPC, but that's a benefit we're trading off against the productivity improvement, let's say. So let me just finish with the non-volatile memory implications, and I'll go quickly through these. So the device and architecture trends are having a major impact. As I mentioned, we'll have an exabyte potential in non-volatile memory in upcoming systems. I think this will create winners and losers, right? There are people who are going to change their codes and be able to take advantage of that. That's really important. The sea of non-volatile memory will permit applications to run for weeks without doing I/O to an external storage system. So I think that if the system is managed in the right way with the right resource manager, they just won't have to do I/O. They can get allocations and run and write data to the non-volatile memory and serialize it out only when they need to. This longer-term productive I/O will be that data that gets written to Lustre or GPFS, and checkpointing as we know it will just disappear. It won't be a certain checkpoint. It'll just be a version of your data structure, and you can back up and get whatever version you want out of that persistent data structure. I think this will change the system design requirements. There'll be an increase in message count, small message counts, looking for byte addressability, for example. Their I/O will be reduced, the demands of that I/O, and then I think it'll change the operational mode of the system. I mean, right now, we've been running systems the same way for like 40 years. We need to think about how these things like non-volatile memory are going to change their operating mode, and that's what we really need to focus on. So just my recap, so finishing up, I think complexity is the next major hurdle. As I mentioned, there's a lot of guesswork that goes on when you have to build a new system, and people have a huge challenge in front of them right now trying to figure out, not only the customers but the vendors, what systems to propose that'll work well on their next generation systems. The memory systems are the thing that I think are actually going to be more difficult, because there are a few standards, there are a lot of new devices, there's a lot of new system organizations coming online. This complexity is going to kill us if we're not careful. There are design tools out there. We're trying to build some of our own. I showed you Siena, and we're trying to work on different programming systems like Dragon, Novel-C, and Papyrus to try to address some of these concerns. They're not the only solutions. We've got a survey out there that we wrote a couple years ago as well that lists a couple hundred different research efforts. So I'd encourage you to look at that too. Again, visit us if you're in the States or you want to come and visit and spend a week or a month. Please do. And thank you very much for your attention.